Hello my dear friends, hope all of you are doing well. As all of us are going through some severe difficulties, please try to understand the current situation and keep patience. Please wear masks appropriately while maintaining COVID protocols. So today in this video I will discuss about the different combination of the capacitors that can be possible in variety of applications. Multiple connection of the capacitors acts like a single equivalent capacitor. The total capacitance of this equivalent single capacitor depends on the individual capacitors and how they are connected. So we can start like the combinations of the capacitors. So there can be two simple and the common type of connection called the series and the parallel combination. There may be some more complicated connections, but they can also be related to the combination of series and the parallel connections. So first we will start with the capacitance in series. So you can see from the figure there is two capacitors C1 and C2, each having two parallel conducting plates, and this plate has the charge plus Q and this one has the charge minus Q. So the left plate of the C1 you can see here and the right plate of the C2 are connected to the two terminals of the battery. This is connected to the battery, and one can see that the charge on the plates C1 and C2 all are the same but equal and opposite for the two plates. So here it is plus Q, so it must be minus Q. It is also plus Q and it must be minus Q. For different capacitors the charges on the plates are equal, that is plus Q and minus Q, I have already told. Otherwise there must be the flow of the charge until each of the capacitor, the net charge for each of the capacitor will be 0. So there must be some flow of the charge. So in the series connection we will conclude that the charges on the each of the plate of the capacitors are the same, so that is plus Q and minus Q. So the charges are the same on the plates of each capacitor, plus Q and minus Q, and the potential drop is the combination of the voltages V1 and V2 across the two capacitors. So this is the biasing voltage, the V. So V must be equal to the add up of the two different voltages V1 and V2 across these two capacitors. So across the capacitor C1 has the voltage of V1, across the capacitor C2 it has the voltage of V2. So it must be addition of the two, the V must be the addition of the two voltages V1 and V2. So we can write it like that: V1 is equal to Q by C1 and V2 is equal to Q by C2, as both the capacitors C1 and C2 has the total charge of Q. Total charge is 0, but in one plate the charge is Q. So we can write it that V by Q is equal to 1 by C1 plus 1 by C2. This is our equation number 1. Now we can take the effective capacitor of charge capital Q and the potential difference is V. So then the effective capacitance, we can assume that it must be Cs, which has the effective charge of capital Q and the potential difference is V. So we can write that the Cs is equal to Q by V. This is the basic definition of the capacitance. So this is our equation number 2. So thus comparing equation number 1 and 2, we can write that 1 by Cs is equal to 1 by C1 plus 1 by C2. So in the series combination of the two capacitor, we can see that the equivalent resultant capacitance is 1 by Cs is for the series combination is equal to 1 by C1 plus 1 by C2. Then in the general term, for the n capacitor in series connection, for n number of series connected capacitors, we can write that the voltage will be add up. So V, the total biasing voltage, is equal to distributed across all the capacitors. So it must be V is equal to V1 plus V2 up to Vn is equal to Q by C1 plus Q by C2 plus up to Q by Cn, where n number of capacitors are connected in the serial combination. So thus we can get that the general formula for the n capacitor, what it will be, 1 by Cs is equal to 1 by C1 plus 1 by C2 up to 1 by Cn. So this is the diagram you can see where the n number of capacitors are connected in series, C1, C2 up to Cn, but all the capacitor has the equal charge plus Q and the minus Q, and this is the biasing voltage V. So in another combination, the capacitors in parallel, you can see this is the two C1 and C2 capacitor and they are connected in parallel, means across their end this is the same voltage, it is mentioned V and V. But in parallel combination we can see there is not the equal charges are there for the two different capacitors. So if across the capacitor C1 there is plus Q1 and minus Q1, I assume that for the another capacitor C2 there is plus Q2 and minus Q2 charge is there. So here the voltage is the same but the charge is the different for each of the capacitor. So voltage across the each capacitor is capital V, and the total charge capital Q gets distributed over all the capacitors. So capital Q is equal to Q1 plus Q2, where Q1 is equal to C1 times V because the V is the same across the each capacitor. So Q1 is equal to C1 times V, Q2 is equal to C2 times V. Now if I put these two value in capital Q is equal to Q1 plus Q2, what I can get? That V times C1 plus C2. I choose the equivalent capacitance in parallel, which is Cp times V. So the equivalent capacitance in the parallel combination of the two capacitor, what I can get, that Cp is equal to sum of the two capacitance C1 plus C2 in the parallel combination. Similarly, for the n parallel capacitors, I can write that the whole charge will add up. So Q is equal to Q1 plus Q2 up to Qn, and the resultant capacitance, what it will be, Cp is equal to C1 plus C2 up to Cn. So we can see that for the resultant capacitance for the n number of capacitors, when they are placed either in series or the parallel combination, so the result says that it is the opposite what resistance behaves for their series and parallel combinations that we have learned before. So there may be some different kind of capacitors in the electronic circuit, and their circuit diagrams are like, there may be different kind of capacitors. So their circuit diagrams are like, one is, say, this is the diagram for a fixed capacitor. So what is the fixed capacitor? It provides fixed amount of capacitance. It means it can store fixed amount of electric charge, so we cannot adjust the charge by ourselves. So it is called the fixed capacitor. And this is the diagram for a polarized capacitor. So this kind of capacitor have the specific positive and negative polarities. You can see this is the positive side, this is the negative side. While connecting such capacitor in the circuit, we should always keep in mind that they are connected in the perfect polarities. So we need to connect such kind of capacitor in the circuit with keeping in mind that they have some specific polarity. So the plus side will connect it to the positive side, and the negative side will get connected to the negative side in the electronic diagram. This is another type of capacitor. It is called the variable capacitor, and such type of capacitor has the capacitance may be intentionally or repeatedly changed. It is mostly used in LC circuit, the inductance and the capacitance circuit, to set the resonant frequency. Sometimes it can also set the tuning capacitor, this type of variable capacitor or the tuning capacitor. So now we will try to derive the capacitance formula of the cylindrical capacitor. So what is cylindrical capacitor? So you can see from the figure, cylindrical capacitor means it has some two concentric cylinder, the spherical, the concentric two cylinder having some same axis. So the inner radius is A, small a, and the outer radius is B. You can see from the figure, and this is the cross-sectional view. So here it is also the inner radius is A and the outer radius of the cylinder is B. So I need to find the equivalent capacitance for such cylindrical capacitor. So I choose the length of the cylinder is capital L, and the charge in the inner surface of the cylinder is the plus Q, and the outer surface of the outer cylinder is minus Q. So I choose on Gaussian surface here. So you can see the Gaussian surface is here. This is the Gaussian surface is here. So it has the radius of R, which is in between the A and B. So I choose the Gaussian surface in between the two surfaces of the cylinder, two concentric surfaces of the cylinder, where the R is L less than R less than B. So this is the criteria. So now the outer and the inner radius, as I have told, that it is B and the A. You can see also from the figure. So you can see the direction of the electric lines of force. It is coming outward from the smaller cylinder to the outer to the bigger one. And I choose the Gaussian surface in between the radius A and B. So here also you can see this is the length. Of the same length, I will choose the Gaussian cylinder of the length L. So from the Gauss's law, the charge enclosed here by this Gaussian cylindrical surface is the capital Q, because only plus Q charge is enclosed. You can see, because in this cylindrical shell only plus Q charge is there. So from the Gaussian law, we can say Gauss's law, that the Q enclosed is plus Q only divided by epsilon naught is equal to electric flux. It means the electric field magnitude times it's in the Gaussian surface area. So the Gaussian surface is a cylindrical one. of the radius it has the r, so it has the surface area of 2 pi rl, where l is the length of the cylinder. So because E and the ds are the parallel to each other, so I get the magnitude of the electric field as capital Q divided by 2 pi epsilon naught LR. So this is the magnitude of the electric field inside this point. This is the magnitude of the electric field. So now the work done to bring some unit positive charge from outer radius B to inner radius A. So this is from here. You can see this line depicts the path of the integration. So you can see I want to take some positive charge from at this point from the outer surface of the cylinder to the inner surface here, from B to A. So the radius varies from B to A. So what will be the work done? It means the potential energy. So the potential is equal to V is equal to minus of integration B to A, the outer radius of the cylinder, to the inner radius of the cylinder, B to A E dot dr. So I can write it like A to B E dot dr. I put the value of E, so it comes out to be, the integration comes out to be Q, capital Q divided by 2 pi epsilon naught L A to B 1 by R over dr. So I can get the potential value V is equal to capital Q by 2 pi epsilon naught L times ln of B by A. So the capacitance is defined as C is equal to Q by V is equal to 2 pi epsilon naught L divided by ln of B by A. So it is better to define the capacitance per unit length in this case. So the capacitance per unit length comes out to be 2 pi epsilon naught divided by ln of B by A. So this is the capacitance per unit length for the cylindrical capacitor. So same before, now we'll try to calculate the capacitance of a spherical capacitor. Now you can see this is the spherical capacitor. So has the inner spherical shell has the radius of small a and the outer one has the radius of b. So I consider one Gaussian surface in between the radius a and b like before. So where a is less than r less than b. So this is the condition of choosing the Gaussian surface. So at any point in between the two spherical shells, so from the Gauss's law I can see that the inner and the outer radius is a and b like before, and from the Gauss's law the charge enclosed by this imaginary Gaussian surface in between the radius a and the b, what it will be, capital Q, because in between a and b only plus q charge is there. I am not considering the outer surface charge minus q because it is outside the Gaussian surface. So from the Gauss's law the charge enclosed is plus q, so it must be plus q divided by epsilon naught is equal to EA is equal to E times A is the surface area of the Gaussian surface. It means 4 pi r square. So I can get the magnitude of the electric field. What it will be? E is equal to Q by 4 pi epsilon naught r square. Similarly, the work done to put some unit charge from the outer surface of the spherical shell to the inner surface here, from this is the path of integration. You can see the path of integration I have written here. So the potential will be V is equal to minus of integration B to A E dot dr. It means A to B E dot dr, because E and dr are in the same direction, so their cross product is 1. It comes out to be normally as E dr. So Q by 4 pi epsilon naught A to B integration lower limit to upper limit 1 by r square dr. If I perform the integration, it comes out like Q by 4 pi epsilon naught minus of 1 by r A to B. So V is equal to Q by 4 pi epsilon naught B minus A divided by AB. So this is the expression of the potential. So capacitance is defined as the C is equal to Q by V. So it comes out to be 4 pi epsilon naught AB divided by B minus A. So you can also see that the capacitance also depends, like in this case in this spherical capacitor also the capacitance depends on the geometrical configuration of the spherical cells, because this is the inner and the outer radius are there. So my friends, I am concluding my discussion here. Hope all of you are following the invisible threads. If you have any kind of problem or any suggestion for me, don't hesitate to let me know in this video's comment section. I'll be happy to help you. Stay motivated and stay safe. Thank you.